Hello, today we're going to be working on polar equations. Reminder, in the past we were working on converting from polar to rectangular coordinates and vice versa. Today we're going to be working with polar equations, converting those to rectangular equations and vice versa. So just as a quick reminder, a polar equation is going to be an equation that has either r or theta or a combination of r and theta as the variables. On the other hand, a rectangular equation is going to be one that you're more familiar with. That's going to have x's and y's in some combination or the other. It could be as simple as an x equal or a y equal as well. So, with that in mind, if you haven't already, take a moment to jot down the homework, and then we'll begin. As we're working on converting polar to rectangular and rectangular to polar, we're using the same toolbox we did in the first part of our section when we were just working with converting coordinates. These come from a basic right triangle with x, y, and r placed appropriately, right triangle with theta as our central angle. So we can use cosine theta as x over r, so x is r cosine theta, etc. And then of course we have Pythagorean theorem that holds. These can be found in your previous handouts or notes. To start out today, we're going to start with a rectangular equation. This, as a little bit of review, is the equation of a circle, center 0, 0, radius of 4, x squared plus y squared equal r squared, coming from a couple previous chapters. Basic tools, here's our ultimate goal. If we're trying to convert from rectangular in terms of x and y to polar, where we can only have r and or theta, we need to think of those tools and figure out how to get rid of our x squared and y squared in this case. And thinking about our tools, I know that x squared plus y squared is r squared. I can simply do a replacement and say r squared is 16. So technically that is a polar equation. It has r or theta or both. Okay, if we were going to actually look at our graphing calculator and set it for polar mode, you'd find that r equal is the general form, kind of like in function mode, it's y equal. So in this case, the question is, should I take a square root or not take a square root? If it's going to make it simpler, yes, I would say so. In this case, the r represents a radius. A positive negative square root wouldn't really make any sense for this. I can take a square root of both sides to say that r equals 4. That's a polar equation. Technically, either of those is fine, and we are finished with that one. Next, we have the equation of a vertical line at x equal 2. All x values are 2, y values are completely unrestricted. Now, knowing I need to get rid of x and replace it with something in terms of r's and thetas, what I'm going to do is knowing my toolbox, I'm going to say that x equals r cosine theta. So I can say that r cosine of theta equals 2. Simple substitution. Now, once again, going back to what we were talking about earlier, our graphing calculator is generally going to have it solve for r, so I'm going to go ahead and divide both sides by cosine to find that r is equal to 2 over cosine. That would be all right. I'm going to take it one step further and say that since 1 over cosine is secant, I could write this as 2 times the secant of theta. Now, somebody may ask which is better. To be honest with you, if you're going to actually put it on the calculator, you'd have to have it in terms of the cosine since we don't have a secant button. So either one of those is fine. Sometimes it's a matter of trying to match something up in the book. Our next equation, 2x minus y plus 3 equals 0, I know is the equation of a line, x the first and y the first. If we solve for y, we'd find it's y equal 2x plus 3, which has a slope of 2 and a y-intercept of 3. So you can imagine what that looks like. one thing you'll find interesting with polar and rectangular, sometimes you'll find the simplest equation in one turns into a ridiculously difficult equation in another. In rectangular slope-intercept form, or an equation of a line is about as simple as it gets. You're going to find as this evolves, it's actually going to look quite a bit more involved. So to start with, we are going to use the same principle we did on the last one. The x I'm going to replace with r cosine theta, so this becomes 2 times r cosine theta, and the y we're going to replace with r sine theta. And knowing I'm going to ultimately have to solve this for r, I'm going to shift the 3 to the other side to make that equal to -3. Okay, now I have two terms on the left side with r as a common factor. So knowing that I can't combine those because they're not like terms, but I do need to have r equal in order to be in the appropriate form, I'm going to factor out an r, and that would leave 2 cosine theta minus sine theta equal -3. So that allowed me to go from this line, where we had two terms with r in them, nothing in common that we could actually combine like terms, down to this one, which allows me to have a single r as a factor, which means I can divide both sides by that quantity, what's in parentheses, to find that r is equal to -3 divided by 2 cosine theta minus sine theta. Obviously much more complicated than the original, but it does allow me to use this in polar form. Okay, our next equation, 3 times x times y equals 9, with the multiplication no longer makes that linear like our last one. So if I were going to actually divide that both sides by 3x, I'd find y equals 3 over x. It's called a rational function, which when you actually graph those, if you recall, look like these. Okay, it's going to have horizontal asymptote and vertical asymptote at y equal and x equals 0, and basically it's going to look similar to what you see there. Now, like the last one, I'm going to go ahead and do my substitution. X is going to be r cosine theta, y is going to be r sine theta. So I'm going to have, actually before I do that, let's do this. Let's divide both sides by 3 to find x times y equals 3. That's just going to simplify matters just a bit. Next, I'll replace the r cosine theta and the r sine theta. So we have r cosine theta times r sine theta. And unlike the last one, these are not terms. There's not addition. So I can rearrange my multiplication and make that r squared cosine theta sine theta. Not the greatest handwriting with my finger, but that's all right. Okay, so we didn't factor out like the last one because it was not addition. We rearranged the factors using commutative property, and we get to this point. Now, our goal is to solve for r or r squared. So I'm going to divide both sides by cosine and sine, and I have r squared equals 3 divided by cosine theta and sine theta. Now, the next question is, do we go any further? If we took the square root of both sides, would it get any simpler? And then, unlike the one earlier where we had 16 is equal to r squared, this one's just going to have a square root of that mess, which is not going to make life any better. Okay, the only thing we can do with this one that's going to make it any better would be maybe to write this as 3 times secant times cosecant, since it's 1 over sine and 1 over cosine. So 3 secant theta cosecant theta, and of course I run myself out of space. But in this case, if I were going to actually graph this on a calculator, I would leave it in that form. So that's okay. If you were going to look in the book, you might see either one of those.